Hello, y'all. This is Darrell Lee Berber Jr. doing some more linear algebra. Be sure to like, subscribe if you haven't, share. There's my X link, my Patreon. Also have the STEM Discord up and rolling. People are starting to join. And you can ask questions there, ask questions in the live chat, and I'll either address it in the comments if it's brief or make a nice video on it if it's more involved. And what we'll do today is I have a MAD homework assignment coming up that's due tomorrow. And I'll finish section 1.5 and start on some section 1.6. May not finish 1.6, may have to do some of that later. First, I will review uh, reducing matrices, the echelon form and the reduced row echelon form, so we can have an idea of what that is, because that's central to sections 1.5 and 1.6, as well as some of the things I'll be doing in the homework. And what I'll probably do is come back Monday or Tuesday and actually work some of the homework problems. So today will be more concepts, examples in the book, and Tuesday, I'll say Tuesday, I'll do some actual problems in the back of section 1.5 and 1.6. But like I said, we'll start with a review of the different terms of matrices. So my current professor says that terminology is a big deal in math. So, and I also often get mixed up with the terminology as well. But as far as the matrices, really, there's pretty much two things you have to keep in mind for it. And let me get the Zoom showing. Boom. So there's mostly two things to keep in mind when you're dealing with the matrices. So you could either have a matrix where you have some kind of numbers. It doesn't really matter what it is. Let's say I have a matrix like this. I'm just going to just put some random numbers out there. Now, if you notice this matrix, there's and actually let me make one more row to make it symmetrical. So let's add, and let's call this 3. Let's call this 0. All right. So if you look at this matrix here, what we have is we have a bunch of zeros underneath these columns, and above here we have, some ones, some zeros, some numbers, but whatever it is, there's still numbers at the top. And let's say we reduce this a bit farther. Uh, let's say we even had even all ones here. Let's see. The important thing is that we have zeros at the bottom and we do not have all zeros at the top. So we can call this echelon form, where there's zeros at the bottom and not all zeros at the top. And we can call reduced echelon form when we have a column of ones and we have zeros everywhere else. So when we have nothing but ones and a bunch of zeros, we can call this the reduced row echelon form. And normally we would have it like equal to something. So let's say this is equal to 1, 2, 3, 4. And let's say this is equal to 5, 6, 7, 8. So, and the way this works is like this. Whenever you have a matrix like this, we're solving for something. So what this matrix would have come from is the general form is you have a matrix, you have a vector, and it'll be times another vector. Normally that vector is called B. So let's say we have, and I'll note the words here. So we have a matrix on the left. We're multiplying a matrix multiplication times a vector, and we're going to end up with another vector. So what we do is, if we was to break this up, we would have the matrix there, we would have the vector there, and then we would have the vector that is equal to here. Now, this is the important detail to keep in mind that makes these matrices make sense. So pay close attention to this. Up here, I have a matrix that is a 4 by 4, so I'll keep that 4 by 4. And if you notice, on this part here, I have a matrix that's 1 by 4 at the end, 1 by 4. So what that means is the matrix in the middle will be basically a mixture between those two. So this matrix is 4 by 1. And if you look at this, the numbers on the outside of here, and I swap these. The numbers on the outside of here will become the numbers that's basically these two here. And the numbers on the inside of here need to match. So that's the way it works. So this is how you can always make sure that your matrices are aligned in such a way where it'll multiply properly. So to highlight it even further, I'll actually write down some values for these matrices. So let's say, remember that the row is going to be here. So this is row 1, 2, 3, 4. That's the row. And the column is going to be up here. So that's column 1, 2, 3, 4. So if I was to name these, this would be A11, this would be A21, A31, A41. This would be A12, A22, A232, A42. And the same thing here, this would be A13, A23, A33, A43. This would be A14, A24, A34, A44. And Suzuki says, what does a matrix actually represent really though? What are those constants? And are they a set, an array of a kind? So basically you could think about and this is actually going a bit ahead, but what it really is, you can say the matrix is a transformation. And that's actually what we're learning at now. And that's actually the foundation we're doing here, which is why I thought it was really a good idea to do the review. That's the foundation here that'll lead up to that. So it's kind of like basically if you have a vector in a certain space, let's say the vector is in 3 space, basically you can multiply that vector by a matrix and you can get it to appear, and this is just random vectors I'm throwing out, let's say you can get it to appear in a 2-2 space, for instance. It's probably a bad number example, but it's just to say that you can take a matrix and you can take this vector and get it to appear in another space. And if you look at it, that's exactly what we're doing here. We have a matrix that's a 4-4 matrix. We have a vector that's a 4-1 vector. But now we have something here that's a 4-1 vector. Now, I happen to pick numbers that's very, it happens to run like that. Let me pick a different set of numbers that may make it more complicated, but that might make the point more. Let's say we have a 3-2 vector. That means that whatever vector I have here, the first thing has to be a 2. Because again, these two in the middle have to match. And I'll show why in a moment. So let's say this is a 2-1. What that means is that this third column, again, is going to have to be the outside of these two, and that's going to be a 3-1 vector. So what this means is that the matrix can take a vector and in one space and change that vector to exist in another space. And that's what's called a transformation. It gets kind of complicated. But this is the basic idea you need to understand to later understand what a vector matrix is and what it's doing. And he says all those A11, A12X, the same as LSE's system of linear equations where they represent the variables. Um, Technically, I would say no, not as I mean it here. Is literally referring to the spot in the matrix. And I'm glad that makes sense. And that's the basics of the basis of the transformation. So basically, if you look at it this way, as far as the A's, we have row one, column one. So that's called A 1 1. We also have row four, column two. So that's why that one is called A42, A row four, column two. And let's say we have row two, column three. That's why that one is called A23. So I'm literally referring to the section or spot in the column. You could almost say that the different rows and columns in the matrix are they have addresses, I guess you can say. And these are the addresses for each of those numbers. So if you're looking at a matrix and your professor says what's the term in the position 2 4 of that matrix, well that's going to be column two, excuse me, row two, column four. So he's talking about this one here, right? And basically that's you could just say the address of it. And this is going to be uh the vector. So we can call this, normally they call it x. So we can say this is x1, x2, x3, and x4. It'll be like that. And we see, so I'm going to stick with the top example since I have that one written out. But this still works as well. Maybe I could just put this somewhere else smaller so it could still be there. So I'll just put that right there as a sort of side example. No need to remove it. Right. So again, that's just showing that if you start with a 3 by 2 matrix, that means you have 1, 2, 3 rows and 1, 2 columns. You're going to have to multiply by something with 2 rows, and I'll go over why that is in a moment. And then what's going to happen is you will end up with a 3 row and 1 column matrix because that's what the outside of those things are. That's just simply how the matrix multiplication works. And the reason why to address similar to the second question. If I was going to multiply this in, I can say that what I'm going to basically do is I'm going to take this matrix, this vector here, and I'm going to basically plop it on top of the matrix. So you can say this is going to be x1, and I'm going to put these here. So that's going to be A11, A12, A13, A14 plus x2, and I'll color code this as well. So let's say these are here. I'll make these purple. Boom. And I happen to call this first column yellow. So that's where I'm getting that from. And then we have the A2 there. So that's going to be A12, A22, A32, A42. And I happen to color that one blue. So let's keep that. And then I call that one orange. So then it'll be x3, and we're going to multiply that by A13, A23, A33, A43, and I'll keep the coloration there. Let me move this over a bit. And then we have the last one, X4. So then, of course, that's going to be the A14, A24, A34, A44. And that's basically how you multiply that vector by the matrix. Let's see what's a good color to make that one. I'll just add another color. So I can not have to duplicate a color here. Oops. Okay. Let us try gray. So we have gray here, and this will still be purple. Now, remember, we needed to end up with a 4x1 matrix, and guess what? If we actually work this out, we'll end up with x1 times a11 plus x2 times a12 plus x3 times a13 plus x4 times a14, and then we'll have x1 times a12 plus x2 times a22 plus x3 times a23 plus x4 times a24. And what I'll do, I'll copy these. Actually, that might make it confusing. I was going to just copy it and change the numbers. Just in case, let me just write it out. So this would be a1, a13 plus x2, a32 plus x3, a33 plus x4, a34. Then we'll have the last one, which will be x1, a14 plus x2, a42 plus x3, a43 plus x4, a44. Now, if you look at this, what will happen is all of these numbers will multiply and add together to be one row. So this will be a number. The same thing will happen with these. They'll add together and be a number. All of these will multiply, add together, will be a number. All of these will multiply, add together, be a number. So what will I end up having? I'll end up having four rows stacked on top of each other, which is a 4x1, 1, 2, 3, 4, 1, which is, voila, exactly what we needed, a 4x1 vector. So this is basically how you handle multiplying these things together. Now, when it gets to the point of solving the matrix, which is the point of showing this, getting to the point of solving the matrix, what will happen is, and I call this number in red, so I'll keep that alliteration. If I wanted to solve, if we have numbers and we have a matrix already, I'm going to literally copy this to accentuate what I'm doing. I'm going to copy this matrix A and put this here. I'll erase some of the extra stuff. I'll keep the color stuff. And then I will copy the numbers on the side. So what I have here now, this is what I called A, and this is what I call the B vector. And when I solve these, what I'm going to solve for is the x's. And why? Because as we saw earlier, this first column here relates to the x1 column. So all I did was just put that on top. The second one here relates to the x2 column. This one here relates to the x3 column. And this one relates to the x4 column. Therefore, what ends up happening is a lot of the times we end up with a matrix that can be a system of equations or what have you, or even a set of numbers. We end up with what is going to equal. And then what we do is when we do the rows, so now this comes into play why we were talking about these, when we actually reduce the matrix to look like this, what will happen is if I reduce it to the form on the left, so let's say I reduced it to the form on the left, right? I'll end up with, and again, I'm on the left side here, I'll end up with x1 plus 2x2 plus 3x3 plus 4x4 equals 1. Then I'll end up with x2 plus x4 equals 2. So you see what I'm doing here? All I'm doing is just plugging in my x values here, but I know that these columns relate to those x values. Then I'm just pulling out what the values are. So it becomes very simple. I know that x3 plus 2x4 equals 3. And then I know that x4 equals 4. So now I solve what those values are. Now, this is the echelon form. The reduced echelon form is called that because if I do this with the reduced echelon side, all I have is just that one variable. So I have x1 equals 5. I have x2 equals 6. I have x3 equals 7. And I have x4 equals 8. So that's the power of the reduced row echelon form because we reduced it as far as we possibly can. And now it makes it very simple to understand what the x values are because, I mean, there's nothing else I have to do. But on the left side here, I actually have to, if I really want to get it to the absolute, lowest, I have to actually solve for a few things. So for instance, I know x4 equals 4, but I have this right here, right? I know x4 equals 4. So I can say x4 equals 4 and so that means that x3 plus 2 times 4 equals 3, which means that x3 plus 8 equals 3. So now I know x3 equals -5. And I randomly pick these numbers, so these two matrices and answers don't correlate between the left and the right side. So just remember these are separate. So these numbers here don't relate to the numbers on the left side. That is made up numbers. But if I did have an actual matrix, then when I solved for these two, then it will equal the same thing on the right side. But again, I just randomly pick numbers now so they don't relate. So let me know how that comes across, Suzuki. Does that make sense? Do you have any questions about this? And then since we review what those are, that basically sets the foundation that we'll talk about momentarily. So I'll just call this a review of echelon and reduced echelon, right? So that's what that is. Awesome. Sounds good. And understanding this will make clear what we're about to go to. So now we'll go ahead and jump to the book. You're welcome. I'm glad it helps. Now, we left off before, we left off basically with uh, this example. So let's see what I mean here. That's the 1, 2, 2, the 1, 1, 2 matrix. And then we progress to this example. You can see how it's the 1, -1, 1. So that was example 3 and example 4. So I'll call this example 4. I'll call this example 3. So and example 4 is on page 57. So what we'll do is we'll continue and round out this section here with example 5. Because you'll be able to see what I spoke about a moment ago in the review. So this is example 5 on page 58 of the book. So what it says is find a Cartesian equation of the plane in R3 given parametrically. Now, the video I did earlier that's called Cartesian and Parametric, I did that one in 2D. And I found out it's much harder to do it in 3D. So in 2D, if you can go to that video, it's called parametric and Cartesian. It'll show finding the Cartesian equation in R2. R3, we actually have to do the row reductions that I reviewed just now. That's why it was important to review it. We have to at least, in math, there's more ways to do things. So it's possible you could do it another way. But the way that the book is showing it here, if you're given a parametric equation, so that's what they're giving us there. They're saying a parametric equation of this plane, because it's in R3, you have two vectors, so it's going to be a plane, is 1, 2, 1 plus S 1, 0, 1 plus T 2, 1, 1. I know that this is the parametric version of it because I have two vectors. I like to call my vectors U and V. And I have my vectors being scaled by T and S. So we know T and S are going to be real numbers, which means that I have a vector SU and it's added to the vector TV, and the scaling of this vector by S is going to, it's going to stretch the vector. Is going to maybe if S is negative, it'll go in that direction. And the same thing, T will scale V, and T might reverse and go in the other direction as well. But what it's saying is if I add up these vectors together, so for instance, this long vector here will be SU plus TV. If I add these two things together, so for instance, if I added the scaled ones here, the red and the green one will end up going longer because they're longer, right? The negative ones in this direction will, they'll be a bit longer, but they'll still be some addition of those two vectors. What that means is if I add every single version of these two vectors together, I'll end up sweeping out an entire area in 2D, so that'll make my plane. So this plane is swept out by those two vectors. If you add up every single version of those two vectors, so that's why it's called the parametric version, because it's literally parameterized version of those two vectors. So what I can do then is go ahead and take this parameterized form and change it back to the Cartesian form. And as a reminder of the Cartesian form is going to be some version of a normal vector times x1 plus, so this would be n2 x2 plus n3 x3 equals some number that I'll just call C. So basically what it wants us to do is take this parametric version and move it to the Cartesian version. And what I'll do is I'll go full screen, see if I can increase this a little bit, and then I'll start working this out and we'll see what we get. So see if I can increase the size of this a bit. All right. And I'll just have this here. You have to remember that the top is cut off just a little bit, but it's good enough to see. So they gave us this parametric equation, 1, 2, 1, S101, T211, and it wants us to ask which vectors B can be written in the form 1, 2, 1 plus S 1, 0, 1 plus T 2, 1, 1 equals B1, B2, and B3, right? And then it says the system of equations can be rewritten, and what they're going to do is simply solve for a constraint equation that'll give us the Cartesian. And what I'm going to do is just work this one out, and I'll see if I get the same answer they get. I might do it slightly differently. So what we're going to do is Now, one difference or one detail here, now we have this added vector on the side. So what I'm going to do is I'm going to bring that to the other side. So now I'm going to have b1 minus 1, 2, b2 minus 2, and b3 minus 1. So all I did was just subtract this vector here from this side so I could bring it to the other side so I can make a proper matrix. And we earlier we covered how really this is sort of like, if you notice, this is very similar to what we did when we divided that out, right? We just took these x's and put them on the sides. So basically, you can see how this is the parametric equation, the parametric version of this hyperplane. And I say hyperplane because it has more than 3 vectors in it. But all they did was this is the exact form of that. So you can see where that came up. And as you mentioned earlier, that's the thing about the book. Sometimes they skip steps and just jump in the middle. But this is how they got that. They just divided that out. So what I'm going to do is now I'm going to basically retract that. And I'm going to say, actually know that I have this matrix here that was divided into these two columns. I'm basically going to pull that out. And now I have this equals b1 minus 1. Let me write this a bit better. b1 minus 1, b2 minus 2, b3 minus 1. Now let's check out our understanding from earlier. We have 3 rows, and we have 2 columns. I have 2 rows, and I have 1 column. So what should I have here? These two things are the same. Therefore, I can multiply them together. I have 3 and 1 on the outside. So let's see if this is a 3 by 1 matrix or vector. So we have 3 things here. So that's 3 rows. And these are, these are subtracted from each other. So these are not just, 2 uh, uh, columns. These are subtracted. So they're going to make 1 column. So that means we do in fact have a 3 by 1. So we know that the uh, uh, what sizing of the rows and columns, they match properly. So now we know that we're on the right page. So that means if I want to solve this thing that we covered here, if I want to solve this thing, I extract the thing in the middle and I just put the matrix and the answer together. So I'm going to do that here. So I have my S and T at the top. I'll just copy this down. So I wrote it nicely. I'm going to have this. Then we're going to just put my answer on the other side, which is this. And now we can see all we did was do exactly what we talked about before, right? So the answer on the right side, those are my S and T columns. So now I know, just like we did in the previous example, when I reduce this matrix, what I'll be doing is solving for S and T, or I can do like I want to do in this problem, and literally, I'm not even caring about, even though I will get a value for S and T, I'm not even caring what the values for S and T are technically. I just want to get some row to 0, and then I know I'll have my basically my limiting constraint on what the plane has to be. So all I'm going to do is I'm going to reduce this as far as possible. And technically, so going back to the 2, technically I do not have to reduce to here. I do not have to go to reduced echelon form. I just need to get some row to 0. That's the name of the game here. In order to find the Cartesian version of the plane, all I have to do is get some row to 0. And what I end up with is this form here that I put it in. And let me actually put my, actually, that was a vector written out, so I don't need a little vector notation on the top. What I end up with is this, except my C will equal 0. So this is what I want. I want to reduce this thing to the point that all of that will equal 0, which means I need to have 0 on this side, and everything on this right side will be on the left side of the equation. So that's what I'm trying to do here. So we're going to do that and see what we get. So the easiest thing I can say is, let's get zeros at the bottom. That's the first thing I could think of. So what I'm going to do is I'm going to say row 1, or say row 3 minus row 1, and I'm going to put that in row 3. So to illustrate, row 3 minus row 1, so there's going to be minus 1. It's going to be minus 2. And this is literally going to be minus v1 minus 1. So I'm going to rewrite 1, 2, v1 minus 1. That stays the same. 0, 1, v2 minus 2. That stays the same. 1 minus 1 is 0. 1 minus 2 is negative 1. And I have v3 minus 1 minus v1 minus 1. You have to put a b there. And typos again. v1 minus 1. All right. So I'm going to simplify this first. So I have 1, 2, v1 minus 1. I have 0, 1, v2 minus 1. And I have 0, negative 1, b3 minus b1, and then I have b3 minus b1, because the b3 will be there. Now I'll make this a different color since I'm doing something different with that. The b3 will be there. It'll be minus 1 minus b1 plus 1, and then we have b3 minus b1, and the plus 1 minus 1 cancel. So if I made a mistake on that, let me know. So sometimes when I'm explaining it out, make a typo again. So this is what I have. So what I'm going to do now is I'm going to say, I'm going to still work on that bottom row. I'm going to say B3 plus, that should be a row, by the way, row 3 plus row 2. And I'm going to make that row 3. So this is going to be 0 plus 0. That's nothing. Row 3 plus row 2 is going to be plus 1. And this is literally going to be plus B2 minus 1. So let's go ahead and do that calculation. I have 1, 2, b1 minus 1. I have 0, 1, b2 minus 1, just rewriting those. Then I have 0, negative 1 plus 1, 0, which is what we were looking for, getting the row to 0. And now I have b3 minus b1 plus b2 minus 1. So what do we have? We have something, a whole row equaling 0, which means that that should be my constraint equation. So I'm going to pull this out. I'm going to have b3 plus b2 minus b1 minus 1 equals 0. So then I would say my constraint equation is b3 plus b2 minus b1 equals 1. And since we are basically putting it in this form, we had a constant on the left side, so it didn't quite equal 0. So C is not going to be 0 in this case. So what I would say is my uh, uh, normal vector, because of course if there's nothing in the front, I have a 1 here, I have a 1 here, I have a 1 here, and let me make a little bit more room for that 1 there, and I have a 1 here, no coefficient in the front, I have 1, so that means my normal vector is 1, 1, negative 1, uh, and now I have my plane. Normal vector is that, and I can see I have x3 plus x2 minus x1 equals 1, and that's my plane in R3. So let's see what the book says and see if I made any mistake anywhere, right? So Looks like I added something incorrectly. What did I add incorrectly? Yeah, negative. Oh, well, there's more than one version. So I think they did different lines than I did. Or did I do a math mistake? Let me see. Oh, that's what I did. Oh my gosh, I didn't copy the number over correctly. So this was actually a 2. So I wrote a 2 there, but when I rewrote it, I wrote a 1 right here. So that was my typo. So just go back and make that a 2 if you made that typo. That was a 2. Uh, and since that was a 2, this would have brought a 2 down when I added that line. So this will be a 2, and this will be a 2. So I just made a typo and wrote that one as a 2. There we go. So it is the same one. And it looks like they changed their signs of things. So I don't know why the book does that sometimes, but that's what they do. So if I take this whole thing and I multiply by -1, and I say -1 times x3 plus x2 minus x1 equals 2 also times -1, then I get the exact answer the book got. So the book got x1 minus x2 minus x3 should be plus x3. X2 minus, minus x3 equals -2. So that becomes the equation for the plane according to the book, which means that according to the book, they just multiplied everything by -1, and they got a normal vector of 1, -1, -1. And that's what they have. So yeah, that looks to be it. So any questions on that? And the question was, what does it give us if we set it equal to 0? Well, I would say that I guess you could say that's the default. So the difference is this. If you have a plane, right? I'm going to just draw a random plane. And actually, I could put this in the same drawing. It might make it even more clear. So this is going to be my x-axis and my y-axis. This is my x and y, my coordinate plane. And actually, let me put it in 3D, actually. So I'm going to make the sort of the one that's coming out here, I'll make that sort of dotted, right? So let me make this dotted. So this is the answer to the question, why, what does it mean if it's equal to 0? And it's actually a very important question, so it's a very good question. But this comes into play depending on what the problem is. So I'll say that this is the x-axis, this is the y-axis, and this is the z-axis, all right? And what happens is if I have a plane, let's say I have the plane, uh, I'm just going to pick some. It doesn't really matter what the numbers is, so I'll just call it a1x1 plus a2x2 plus a3x3 equals 0. What that means is that this plane, I'll make it the blue plane. This plane is here and is going through the origin. So they call that a homogeneous system. So that means that this plane, wherever it's oriented, there's some point on this plane that goes to the origin that equals that value. So there's some point x1, x2, x3 that equals 0, 0, 0, and it is on the plane. This point is on that blue plane. But if I have, let's say, let's say n1 x1 plus n2 x2 plus n3 x3, and that equals c, and c equals not 0, and c is a real number. What that means is this plane, however it's situated, it is not going through the origin. And I wanted to make it a bit more lopsided there. So this is that plane. But this plane is hovering somewhere to the effect that there is no point. There is no point on this plane that satisfies this equation, whatever it is, where x1, x2, x3 equals 0. So 0, 0, 0 is not on this red plane. So that's the difference. So if it's a homogeneous system, the plane goes through the origin. If it is non-homogeneous or heterogeneous, then the plane does not go through the origin. And however it's oriented, depending on how this normal vector is, this normal vector will determine how it's oriented. However it's oriented, it does not go through the origin, so it's non-homogeneous. So that's the difference. So what that means is this plane that I have here, we don't technically have any numbers for it. I mean, I could put the numbers in and plot it, but it's not necessary to do that. But whatever this plane is, what this is saying is this plane is somewhere where it does not go to the origin because where it's hovering at is, let's say, here somewhere, and there's no point on that plane that goes to the origin because it's x1 minus x2 minus x3 equals negative 2, which is the form of it that the book has. So it simply means that this plane is not going to the origin; it's shifted some kind of way. My professor calls it a lift. My professor calls it a lift. So what he's saying is this plane is lifted so that it doesn't go through the origin. So that's the difference. So why don't we take one more look at this section and see what we have. So it's saying uniqueness of solutions, right? Definition of a rank. Let's actually make a note of this because my professor made a point to talk about that. And by the way, how does that sound, by the way? Does that seem clear? Kind of like that, yes. I don't know if the word transform would be good because my professor's really big on terminology. I've never heard him say transform. He always said lifted or shifted. So I would say this plane that goes to the origin is homogeneous because it goes to the origin, and I would say this plane is lifted or shifted away from the origin because it equals some number where C is not 0. So transformation may still work, but in my I'm still learning, so I don't want to say something my professor didn't say. So I would suggest lift or shift, and that's what that means. And it's awesome. That's that. And the rank, talking about the rank, important concept that deals with how many pivots we have. So if we have, let's say, this, again, I'm just making up numbers. We have this and we have 0, 0, and we have, let's say, 2, 1, 3, for instance. And let's say we reduce this thing as far as we can because whatever we do with the third column, I don't imagine we can do something to make that equal 0 because if whatever I do, adding or subtracting this column here, I'm going to add something over there. And whatever I do, adding or subtracting this one, I'm going to add something to this column. So we could assume that we reduce this as far as we can. So what this means is that this has one pivot. This means it's a 1 with a bunch of zeros. And this has a pivot. And so that means that this matrix, I would say, is rank of A. If I call this matrix A is 2. So this is matrix A. So definition, it says the rank of a matrix. Oh, that's horrible writing right there. The rank of a matrix A is the number of non-zero rows the number of pivots in any echelon form of A. It's usually denoted by R. So I guess it means that I probably can do this. Rank RA equals 2. That's my understanding of that. And it says any form. So I guess that refers to the fact that, so let's say if I had a matrix like this, it says any form. So if I had 1, 0, 0, 0, 1, 0, 0, 0, 1, technically the rank of B, if I call this matrix B, should equal 3 because I have 3 pivots. So that's what I'm understanding of this. And this is pushing the edge of my understanding because we're on this right now. And but like I said, I'll be doing some homework on this. So by Tuesday, I will understand it was enough to actually demonstrate my homework problems. So I'll come back to it on Tuesday and we'll look at the actual homework problems in the back of the book. And I believe the one this time don't have many answers, but I really don't see anything we did specifically with rank yet. I mean, because whether I call this a ranked matrix or not, I can still go ahead and say, if this was equal to something, I can still say x1 plus x3 equals whatever, and I can still say x1 equals whatever. So I'm not really sure what the relevance of the rank is, other than if I'm describing a matrix to you, I could just say uh, a matrix that has so many pivots that work really well. But maybe that'll come later. A lot of times I understand in math thanks, I appreciate it. Yeah, it's going well so far. So far I made a 100, like a 100 on the first homework, a 100 on the second homework. This would be the third homework. I believe he drops one or two. I'm not sure. I have to look at that. But usually these classes, they like, let's say if they give you 10 homework assignments, they say, well, we're only gonna count 8 homework assignments, and then they like drop a homework assignment or two. So it's possible that he's going to drop one or two anyway. But so far, I made 100 on all of them. So I'm doing pretty well. So I'll do my best to make 100 on this third one as well. And this third homework is going to be the homework that the next exam is based upon. Well, technically I share it by doing the assignment. So like if you go to the problem videos I put out, those are the homework assignments. Like he literally goes to the book and says, okay, for homework 1, do problem such, such, and such. And then for homework 2, do problem such and such and such. And that's what it is, that's what it is. So for homework 3, he's like, I don't remember the numbers, but he's like, for section 1.6, do problem such, such, and such. For section 2.1, do this problem. And I'll just go ahead and just go to the book and just do those problems. So you can look forward to that on Tuesday. But I want to make sure I have enough time to do them, feel confident about them, because some of them don't give you answers in the back of the book. But so far, by the time the due date comes, I seem to understand them pretty well since I've gotten 100 so far. And that's that. Let's look at this proposition, by the way. These propositions usually mean something. It says proposition, and what I'll do, we may not actually get to 6 today. I'll probably end at an hour, so that's about 5 more minutes. So maybe I'll finish this proposition here and look at a few more sections, and then I'll just come back on Tuesday and do some of the problems from 1.5, just like the problems start here, and maybe start 1.6 later in the week. And that'll give you some time to catch up on the earlier sections as well. I know you have the earlier sections to catch up on. So that's what I'll do here, and I'll end in a bit. But I do want to look at, where did that proposition go? Proposition 5.1. I do think I remember my professor mentioning this. proposition 5.1. It says the linear system ax equals b, ax equals b is consistent if and only if the rank of the augmented matrix equals the rank of A. Okay, so the augmented matrix, which is basically if you take, so basically it's like mathematical jargon of what we did earlier, but you know how to do this. It's just they're using different terminology. So basically we wrote out all the values for A here and all the values for X, and then we had all the values for B. And then I took and I had A here, and I put the X's on the top and said they relate to a column. And basically what I did was I took B, which was this last column, and said, okay, we're going to solve for this stuff. All they did was take that same thing and put it in this form. They call that an augmented matrix, which is a terminology I forgot myself, so that's probably why I didn't highlight that. But that form is the form of an augmented matrix. So then what that means is this is an augmented matrix if I just, add my B's over here, B1, B2, B3. And now I have my augmented matrix. And then when we solve it, we get some pivots. And in particular, when a rank of A equals M, the system will be consistent. So usually when it has a size of a matrix, it says M dot N. M is the rows. So, okay, so what that means is we have to have a number of solutions equal the number of rows. So if I have a matrix and let's say I reduce it to reduced echelon form, and these are nothing but zeros, and now I have B1, B2, B3. So now I have X1 equals B1, X2 equals B2, X3 equals B3. So that means this is consistent because the rank equals the number of rows. And of course, I know this is a three rank system because I have three pivots. And I'm assuming this is a three column. I'll write it specifically. This is X1, X2, X3 when we pull the values out. So I have a three rank matrix. I have three solutions. So that means that this matrix is consistent according to proposition 5. So awesome. So seems like a good place to stop. Some good stuff to chew on. I would definitely suggest going and review this matrix stuff and how we multiplied it because I mean really that's pretty much the heart of it, especially when we get to um, multiplying matrices together. So it's important to understand this because multiplying matrices is like that's like this on steroids, right? So what I'll do is the next video I make when I do the homework, I'm gonna have to review it because the homework has to do with that. So just make sure you understand this really well. And then when I come back on Tuesday, I'll do some homework problems and I'll talk about multiplying matrices together, which again is this process on steroids. So make sure you have it. So awesome. Thank you for showing up. Thank you for joining the Discord. You can keep on chatting and like, subscribe, share. I know you subscribed already, but like and share. And I'll see you Tuesday. I have classes and stuff on Tuesday or during the week, so that's why I can't be here early like I could do today on Sunday. So that one will be the later time. But again, if you can't make it, the recording is there. But hopefully you can make it. But what I'll do is on the weekend, I'll make sure I do an early one so you can make it. So I'll look for you on Tuesday. If not, I'll see you on the weekend, and I'll see you on the Discord chat. So see you then as well. Have a good one.